Everybody, how are you doing? Nice to see you today again, and today we continue our work and we are working with so-called vectors. I think if you had physics at school, you know what is it vector, because you define vector is a sector which has direction or directed sector or directed interval, maybe you said. And usually we use vectors for two-dimensional space, 2D space. Consider as a vectors the arrow, or 3D space. 3D space, we had the x, y, z coordinate system, and we know that this vector, it is x, y, z coordinate system, and here we have some vector a, maybe, which is located in our 3D space. All vectors according to our school course, maybe it's new for you, I don't know. It has the tail point, the origin or beginning of the vector, and the head point. A head point as a point of direction. A head point. For the notation of the vector, we use small letters and bar or arrow above the letter. So it is a vector. Vector. We can use B vector here, etc. All vectors, they usually have components. Vector A has components. For example, we use the curve parentheses or brackets for 2D space. Two-dimensional vector, we have ax and ay components. So we have for 2D space. Or for example, I denote like b vector here in 3D space. It has bx and by and bz coordinate components. 3D space. Here we have components. Components, they are numbers of functions or some other operations, maybe operators, or sometimes we can use the puzzling situation. Then components of the vector, they are matrices. Components of the vector. Components of the vector. In the very common situation, I'd use here, for example, vector C. We use like numerated components, C1, C2, C3, and we can work with ND space, Cn components, ND space. Nobody forbids to work in ND space, I think. Okay. Obviously. Okay. For example, we have 2 points. A is a tail point here. We use arrows to draw down the vectors, and A point has coordinates, for example, 2, 3. Example here. And tail point, head point has coordinates, for example, 5, 7. To define vector A, which connect to points B and A, and this vector has tail point at point A and head point and at point B, components of the vectors, it is very easy to calculate. You have to take away from the head point coordinates, tail points coordinates. Head minus tail. But this is kind of the main formula. And we have here 5 minus 2, 7 minus 3. And this vector has components 3, 4. Okay, but you can consider an inverse vector B, which has contrary head point A and tail point B. And you can notice here that it is 2 minus 5 and 3 minus 7. And it has minus 3 and minus 4 components. Despite of the same length, these two vectors, they are not equal, and they are opposite vectors. They have different opposite directions here. So we can say that A is not equal B. And the generalization of this approach gives to us this one thing, that vectors A can be equal B if components of the vector A are equal to the components of the vector B. This is the first one conclusion here, and the second one conclusion: components of the vector A can be defined like according to this approach. That's coordinates of the head minus coordinates of the tail point. Tail. Okay. So let's consider some examples here. For example, A point equal has components, coordinates 2, 3, 5, and B has components, coordinates minus 3, 0, for example 10. Here we have A vector B point here, and vector A is a vector which represents the sector which connect A and B point and has direction from A to B point. Sometimes people denote this vector like AB vector, so they put tail point as the first one from the point from which the vector origins, and B point here is a directed point. And to define the components of the vector A, you have to take from the coordinates of the point B coordinates of the point A. So head minus tail and we have here A, we have tail, B head, so we have -3 -2, 0 -3, and 10 -5. Consequently, we have -5 -3 5 coordinates. Okay, so we can say here two main conclusions. If you want to define the components of the vector, if you know 2 points, you have to take away from the head point, the tail point's coordinates. And the other one, the denotation of the vectors, you can use a small letter here, like A, small, or we have the alternative denotation. We can use the letters which identify the points, the given points A and B, and put there in order. The first one according the tail and head location. Okay. There is also one concept, that is length or magnitude of the vector. Magnitude of the vector. So if vector A is a given vector with components a1, a2, a3, an, length of the vector, we usually use the or magnitude of the vector can be defined like square root or a summation of the raised to power 2 components of the vector. This is the sequence of the Pythagorean theorem. And now we can check. We can use some example here. Firstly, consider some examples. For example, vector A has one component, just 2. Its length or magnitude is square root of 2 raised to power 2, and it is the root of 4, and it is 2. First one. The second one, for example, A has a bar, has components. It's bed curved 2 minus 3. Its length 2 raised to power 2 plus minus 3 raised to power 2, and we have here 4 plus 9 square root of 13. This is the answer here. The first one, operation, is multiplication by a scalar, quantity. By a scalar quantity. Okay, A is a given vector. It has some components. Lambda is a scalar. Scalar, it is a special term. It means some non-vector and non-vector mathematics element. Usually it is a number, but sometimes it can be a function. So multiplication by scalar, it means that you have to multiply all components of the vector by this given number. Next one, our work is example. Our examples. Lambda, for example, equal 0. A equal, for example, 2, 1, 3, for example. Lambda A equal, consequently, 0 times vector A, and it is 2 times 0, 1 times 0, and 3 times 0, and it is 0, 0, 0. By the way, this vector with when all components of the vector zeros usually is known like zero vector. Zero vector, it's better to use this denotation, a zero vector. Zero vector. Vector with all zero elements. This is the first one here, example. And for example, lambda equal 3. 3 times A gives 3 times 2, 3 times 1, 3 times 3, and it is 6, 3, and 9. So, one of the conclusions here that a result of multiplication by a scalar gives us vector. The result of multiplication is a vector. Maybe I'll give you one more thing here. You can notice here that if the length of the vector is, I do not like A, then the length of the vector multiplied by scalar gives you L times A. So multiplication by scalar what does it mean? It is stretch or squeeze the given vector. And before I give some very special ideas, I give you the third one. Example, for example, lambda x square. So you can notice that x square is not vector, it's kind of some function. So x squared, but it is still the multiplication by scalar. X squared times a vector gives you 2 times x squared, 1 times x squared, 3 times x squared. So this is the result of multiplication. Multiplication by scalar, if lambda a equal new vector b, so if lambda is positive, vector b has the same direction as a vector A. If lambda is negative, less than 0, b has an opposite direction. So multiplication by a positive number keeps the direction of the vector. A multiplication by a negative number, what does it mean? Inverse turns into inverse vector if it is about direction. An opposite direction to the a vector. If the absolute value or magnitude of the lambda is more than 1, the multiplication lambda a, it is lambda a, lambda a thing. What does it mean? Vector, the result is superior to the given vector, so it is kind of a straightening of the vector. So it is more than length of the vector a. If it is less than 1, multiplication by a scalar reduce the magnitude of the vector a. Okay, that's all about multiplication by a scalar. Next one operation, it is addition of the vectors, the sum of two vectors. All the vectors. So if vector a has components a1, a2, a3, an, and vector b has b1, b2, b3, bn components, addition of two vectors gives new vector. It is in vector c, which is component are a1 plus b1, a2 by plus b2. So you have to add all components correspondingly. an plus bn. Okay, example here. For example, vector a has components 1, 2, 3, and vector b has components minus, for example, 2, 0, 5. Addition of two vectors a plus b gives 1 minus 2, 2 plus 0. I took into account a lot of rule that 1 plus minus 2, it is 1 minus 2, and 3 plus 5, so it gives minus 2, 0, 8. This is the new vector here. Okay. Maybe you have a question. What does it mean? If you have the sum of the vectors or addition of the vectors, can we subtract vectors? What does it mean? A minus b. Can we calculate subtraction of the vector? Yeah, the answer here is yes, we can, but it seems to be like a trick, like addition of the vectors. So a minus b, a bar minus b bar equal a plus minus b here and it is the same like A plus minus 1 times B. So we can consider the subtraction of the vectors as an addition of the vectors or sum of the vectors when the subtracted vector A keeps the same, but the vector which we have to subtract, we just multiply by minus 1. So for example, for given example, if you want to calculate A minus B, we have to make this one thing: A 2 3 plus minus 1 times minus 2 0 5, and the same thing like 1 2 3 plus 2 0 minus 5. And now we can just add them as we did before. But if you have the subtraction of the vectors, it's easy to calculate just taking away the components of the vector B from the components of the vector A here. Some graphical interpretation. Graphical interpretation. Okay, for example, lambda A. Lambda positive, for example, and more than 1. So if vector A is this one vector A here, then lambda A is a new vector which has the same direction, but its length is different from the length of the A by the factor lambda. So here we have kind of a stretching of the vector. If lambda less than 0, but its magnitude is more than 1, we have this situation when A vector is here. Vector lambda A has an opposite direction, but the length is more than the length of the vector A here. Your home assignment here, you have to draw this situation with two situations, then lambda less than 0 and its magnitude less than 1, and then lambda positive but its magnitude less than 1. So you have to make this schematical view of these two operations here. It's your homework, your individual work. You can make this. Okay, homework. Work here. Okay. And the last one thing, graphical interpretation. Graphical interpretation of the sum of the vectors. Okay. There are two different rule approaches here. I use this green thing here. Triangular rule. Triangle rule and parallelogram rule. For example, you have here vector A and vector B. Vector B. And I want to calculate A plus B. Okay, triangular rule. You have to take vector A here direction. Take vector A. I keep the same direction, the same size a given vector here, A bar, and take the tail point of the vector B and align the head point of the vector A and tail point of the vector B. And then the result of the sum of these two vectors, I use the green ink here, is a vector which connects the tail point of the vector A and head point of the vector B. This red vector is a vector A plus B. Okay, so, and parallelogram rule. You have to the same vectors A plus B. I try to make the same vectors. Vector A and vector B, B vector, A bar. If you want to define the sum of the vectors, you have to make to align the tails point of the vectors A and B. This is direction of operations. Directions of operations. And add new side, copy this A to the head of the B vectors and B to the head of A, and this parallelogram, the diagonal of this new parallelogram, gives you vector A plus B. Since that we have the same operation, this blue A plus B vector and this red A plus B vectors, they are the same vectors. If A and B, we keep the same vectors during our operation, but these two graphical interpretation of the summation or sum of the vectors. You can use both of them. But sometimes, for example, for physics, it's better to use one of these approach. For example, triangular rule is better to use if you try to define the root of the motion of the body. For example, if your body, if some given body, some subjects moved along vector A and along vector B, finally we have that these like an equivalent to the motion along vectors A plus B. For example, if you try to make a decomposition to get to the decomposition of the forces, it's best to use the parallelogram rule to define the common force of D, which acts on the body. Okay, so here we have triangular rule and parallelogram rule, and you have your homework, individual work here. Homework. Try to make schematically, use schematically triangular rule and parallelogram rule. Use triangular rule and parallelogram rule for A minus B operation. A minus B operation. Okay. See you next time.